Hello everyone, welcome to the last class. Today we have the last discussion session. I will wait for the students to join, but before that, I would like to go through the acknowledgement, like whatever I have used for these classes. I would like to. This is the tutorial 8 for 22nd April, which is the last class of week 8 of Nuclear Astrophysics course. And I would like to acknowledge NPTEL team and Nuclear Astrophysics course Professor Godicity for everyone and whole NPTEL team for giving me this opportunity to take this nuclear astrophysics discussion sessions or tutorial sessions. And the course content which is followed here is of course according to the nuclear astrophysics course by Professor Gauri City of IT Roorkee. And books which are recommended for this NPTEL course, those books I have followed for preparing the notes and all those stuffs. And uh, then and those recommended books are shared with you in the first class, that which books we are going to follow. So, and apart from that, I have taken help of Wikipedia. Obviously I have shown you various photos, and I have given all the courtesy to all the owners of the photos, that whoever is the owner of that photo, because to make the contents much more improved and much more understandable to the students, I have used many online versions of many things, and I have searched many things are searched and used for this course materials, which I think which are subject matter to copyright for someone else, but I have used them with the courtesy with giving the courtesy. And whatever I have used this pictures and all the stuff, those are not of my own. Obviously I have used from the class, from the books, from the course, and from internet search. So after reading all those materials and checking all those materials, I have created, or I have designed my own materials, that how can I run these tutorial sessions to make it more successful. So that is so I declare that I have used many materials from many things and designed them by own to run these tutorial sessions. So that is the acknowledgement that I want to convey at beginning of this last class. So after that, I will start the class after students join. Hello students, welcome back to the class, and today is our last class, week 8, and I will start within 5 minutes. Let us wait for other people to join. Okay, maybe let us wait for another 2 minutes. I'll start at sharp 5:05. All right, let us start today's session. So, hello everyone, welcome back to the last class or last tutorial session for this nuclear astrophysics course. Next Saturday, that is 29th April, you have your examination, and all the best for that. And today we will do some problems, obviously, and then we'll revise all the topics that is covered in these discussion sessions. And before that, okay, what is my plan? Before that, I will go to the slides to show few things. I'll start with that, and then we'll solve the problems, and then we will do the revision. And at in between or at the last, I want to discuss with you guys that how is your preparation going on, and how are you feeling, how for your examination, and what are the stuff that you want to maybe discuss or share. Yeah, so then that is very important thing, because today is the last day, and that is very important to discuss or to know for me and for you as well. So yes, and as I used to say in the first few classes, that for the Google Drive folder and the YouTube channel, in previous classes I did not mention about this, because these are the thing that you have already known by now, I think. And but still, today is the last class, so let me tell all those things once again, because if you are giving examination, then those will be helpful. That is the recorded sessions, those are there in the YouTube channel, which I have shared the link with you. And study materials, those are given in the Google Drive folder. Google Drive folder. And Google Drive folder is already whoever has the access, I have given access to few people whoever has mailed me or given me the email ID, those. And now due to the examination purpose, I have given the permission to anyone with whoever have the link with him or her, they can access. So again, but those who have already the access, they can access anytime after this course and all those things. But those for the examination purpose, I have given permission to all, but maybe after the end of this whole semester, I will again I'll stop that permission. And but yes, those who has the given permission from my side, they can access it for any time, or after the ending of this course also. All right. So let me start, and I will first start with the start with the slide. That officially this is the last class of the nuclear astrophysics course, and I am your TA Nilakshi, and and this is the week 8. And this in this week, the topics which were covered by professor was the detectors, part 2, then the activity methods, kinematics 1, kinematics 2, and time of flight method, and indirect methods. These are all is nuclear physics course, not at all nuclear astrophysics course, rather nuclear physics course. So these are like very standard things, and those are covered very well with mainly the kinematics part, that is covered very well in the classes. So that is covered very well in the classes, so that I will not go into the details again. And as you can see that in your this time, I will not discuss the questions which are already given to you for the assignments. Rather, I will solve previous year's assignment date, because those are not similar to this year. So that maybe that will be helpful for this time. That's why I have chosen that. And yes, so that we will do after some time. And before going to the further things, I would like to acknowledge from my side to all the participants and all the all the participants who have registered for this course and who have participated in the discussion sessions. And I am very happy that you guys were active enough. People have sent me questions, I have discussed with them, you guys have discussed with me in the class during the classes. And it was some sort of a very successful course that's in that manner. And I would like to acknowledge NPTEL team and Nuclear Astrophysics course Professor Gauri Sethi for giving me this opportunity, as well as to run for helping me to run this course. And books, as those are already shared with you in the SWAM portal, and also the recommended books are given in the first class. I have told you that. And apart from that, obviously, I for teaching you guys, I need to study, and for that thing I have used Wikipedia. Many photos I have used, many things I have searched, many materials I have used. All those are courtesy are given to them, because no pictures I have shown from my side. All those are taken from somewhere or something. But those the photos which I have shown, that about the stars, galaxy, all those things like which were taken by cameras, those are by like me and my group. All right. So for that, I want to declare that I have used many materials and designed them by own to run these tutorial sessions. And what is the thing that I will do? We will do today is that we will do revision, that is very important at the end of this course, and we will solve questions regarding the week 8 contents, that we will do first. And we'll do first. And so after, maybe many of you have already joined, so I can start because it is already 17:11, that is 5:11. So all right, so let me start by discussing the alpha decay, beta decay, and gamma emission once again, because these things are quite very basic things in this course. And I have not discussed alpha decay, beta decay, gamma decay in that, like what are the difference between them in that manner, because I thought that it is basic enough that you guys know. But somehow I found that maybe I should discuss this once again. So for that reason, I am just showing these two slides, and then I am go to the problem solving part. So there are nuclear decays or nuclear radiation, which happens mainly due to the three types of decay. Those are the alpha decay, beta decay, and gamma emission. Alpha decay means the radiation in the radiation process which is emitted here is the alpha, that is the 2He4. That is 2He4. And if you see that the generic equation, then you can see that ZXA, if one alpha particle goes away, then it will be -2 and a -4. The isotope of that X, not isotope of the X, sorry, rather a new daughter nuclei will produce. So as it is modeled here, like it is a parent nuclei and it is a daughter nuclei, alpha particle goes and the daughter nuclei generate. So now the beta decay here, it is an example of beta minus decay, beta plus decay, that is a positron decay is also possible. But here I have shown only the simple example of the beta decay, which is -1 beta 0, that is the -1 E0. If one -1 E, that is it goes from the beta particle goes out from the parent nuclei, then which we call the beta decay. Then the gamma emission. Gamma emission is you know that it is photon emission, nothing else. And this is just due to this happens just to the excited, when there is some nuclei with then some excited state, then then which kind of radiation is happening is called the gamma radiation. And this is very important. And gamma ray actually it can penetrate, it has very high penetration power. So if you say that if you are you are seated over in a room, inside a room, and you are thinking like there is no gamma emission that is hitting us. No, that is not true. That gamma emission is always happening and gamma emission is also always hitting us. It is very rare case that it will not. We are always like taking shower of these rays. So, but yes, alpha beta, that is very they have less penetration power. Like alpha has very low penetrating power, and beta has intermediate, but gamma has very high penetrating power. And we can only do the shielding with the lead if we can do that. And if the lead shielding is also of 2 inches, then only can gamma radiation can be shielded up to some certain up to some certain order. Okay, but alpha particle can just be shielded with the paper skin, beta can be shielded with the aluminum, gamma with a 2 inches lead. So and mass, you can see that gamma is, it is a, like photon has zero mass, it is energy only. Alpha is 4 AMU. These are all given in the AMU. To and you can understand from these also that alpha is much more higher massive particle than the beta. Okay, so alpha, beta, gamma, that I discussed, because other than that, the the types of particles like the quarks, bosons, leptons, and the hadrons, all baryons, all those I have discussed with you in the previous discussion session. If anyone has not followed anything, then all the discussion session are recorded. You can visit, and you can also check the course material that I have used. Those are all in the Google Drive folder. All right. So this was the some sort of week 8 introduction course, introduction theme, and the dynamic whatever we do in these sessions in these week 8 contents, those are the kinematics, activity methods, and detectors of all these type of decays only. Like there is radiation which we are detecting with the detectors, activity methods like what is happening in these reactions, that those activity methods we are studying, the kinematics like whatever, like any reaction or anything. If you consider in case of classical mechanics, like two particles colliding with each other, that is also a kinematics problem. Similar kind of problems is similar kind of problem it is treated for the nucleus things also, and this is called the kinematics of the nucleus. And that is actually the equations were formed in detailed, like for this for this time at least. Like I know that previously many topics were there which were not which was introduced just without any mathematical description, but this time kinematics 1 and kinematics 2, these things were given with the mathematical concept, so I will not go to there. And the kinematics 1 and kinematics 2 is nothing but like whatever we do for the classical mechanics things, like the conservation of energy, momentum, all those things happen only here we are doing. So I'll go to the problems, and we'll do carefully these problems, because these problems are like one is related with the other. Like if we do the first one, then second question will go to the go in the flow of the next question, because I have given this first this was given for the previous time assignment, previous year's assignment, and I find that this is a one approach that maybe which is not covered for you, and you may get this kind of question also. Like some question is given in the first question, and second question is a follow up of that question, so that may also happen. So that for that reason, so the first question which is it is telling, let me go through the question, and let me start with the question answering session. All right. So the question one is saying that outer layers of the stellar environment consist of protons and trace amount of 12C, that is carbon 12, oxygen 16, and other elements. Gamma rays from solar flares had long been observed using satellite-based gamma ray observatories. To study the interaction of protons with 12C, that is 12 carbon, an experiment is being performed. A milder target foil having a thickness of 2 milligrams per centimeter square is bombarded with 10 mega electron volt protons. Calculate the number of 12C nuclei present per centimeter square of the target foil. These are standard questions which you need to know that how to solve this type of question. Otherwise, it will be difficult, I think. I don't know that if this kind of question is already given there in your assignment this time, but I think it was not there. So let me go through one by one line. The first three lines, whichever it is given, those are like not, we are not going to use that. Those are just given to manipulate you, that you will be exhausted just by reading three lines, but there is nothing in those three lines. The last line is important. It is saying that a milder target foil having a thickness of 2 milligram. So first let me write the information that is already given there in the question. So it is given that a Mylar target. So Mylar target having a thickness. When you will solve the problem, maybe you can also write like this. I used to write the information that is given here first, then I start solving the problem. So the thickness is of 2 milligram per centimeter square, is bombarded with 10 mega electron volt protons. Suppose this is the target, bombarded with protons of energy 10 mega electron volt. This has some thickness of 2 milligram per centimeter square. Calculate the number of 12C nuclei present per centimeter square of the target foil, and it is for 12C. That is important. And this is 12C is a standard thing which in case of when we calculated the 1U, 1MU, all those things, everything is actually calculated in terms of 12 carbon. And for that reason, though it is not mentioned here that within which amount of molar mass we need to calculate this, we will consider as 12 gram mole, because 12 gram per mole inverse, because as the 12 carbon is the standard thing, so we consider it is corresponding to that only. 12 is to directly 12 gram per mole. But if you are calculating for other things like oxygen or something else, then you need to do that 12 by 16 into the those things you need to do and calculate that what amount of gram per mole you have in within which you want to calculate. So so mostly with whatever you can expect in the questions, that will be based on the 12 carbon base. Now let me solve the question that percentage mass like of carbon 12, in Mylar is equal to 62.5%. That is an information either you need to remember, or you can, or this will be provided to you. But here in this question it was not written because it was already told in the class. But otherwise you need to
Ma'am,
yes.
uh, I just want to asking this question. 62.5%. How 62.5% mass of carbon?
Because the Mylar target is C10H8O4, right? If now you calculate the total mass of this, from that calculate the C10 thing only. If you find out the fraction of them into 100%, then what you will get is the percentage of carbon in the Mylar target. That is the process to calculate it, but otherwise you can remember it.
Okay.
So that is the mass percentage of carbon in Mylar, or I think I don't know. I that much rigorously I have not gone through the videos this time because of some works, but I think Mylar target was introduced to you in the due course. That's why I am not going to those things. So this is the first point that you need to calculate or you need to do. And you can calculate. I hope you can understand that if you know the whole thing, that what is the mass of it, then you can calculate this mass of this, because I have calculated the mass fraction, mass, all those things in the third class or something like that all. And also I have shown that what is the transfer between one u or mu, and then energy mev, and in terms of C square, all those transformations are very important. You need to revisit those again and again. And I go when I thought that, then I went through that very rigorously, just because you don't get stuck into those things, because the units are little bit very weird, and units are some things which you need to uh, learn in this course, because these are some sort of different kind of units, and you are tackling both units at the same time at the nuclear level, that is the micro very quantum level, and as well as the astronomical distances. So unit is very important here. And then it is told that then it is told that a mylar target foil having a thickness of 2 milligram per centimeter square thickness is bombarded with 10 mega electron volt protons. 10 mega electron volt protons. Calculate the number of now. Now you know the thickness of this material, the mylar target, and it is you need to calculate 2 milligram per centimeter square thickness of foil contains how much amount of carbon. And then you need to calculate number of 12 carbon nuclei present per centimeter square of the target foil. So this is the ultimate answer that you need to calculate, as it is told that calculate the number of 12C nuclei present per centimeter square of the target foil. Now the thing is that number of 12C nuclei present is it will be calculated as Na, that is the Avogadro number, because and it is per mole inverse, into the number of how much amount of carbon is contained in 2 milligram per centimeter square thickness, that is you can consider as mt. If we consider this, then it is mt by the 12 gram per mole inverse, as it is called, as it is told about the carbon thing. And I told already that carbon is just like the corresponding thing, like if it is carbon, then you can directly consider 12 gram per mole. So you need to calculate this number of 12C nuclei present per centimeter square of the target foil. So the Avogadro number that you know that it is 6.023 into 10 to the power 23 per mole inverse, per mole or mole inverse. Then the MT, that is the number of thickness of the foil, contains how much amount of carbon. Now what do you need to do to calculate that? You know that the mass of 12C in mylar target, and that is a 62.5%. So if you in a singular thing, like in a single thing, if it is if you consider the totally a 100% thing as one, then the 6.25%, 6.25 is the amount that you will get as 62.5 is the amount that you will get as a carbon. So if you calculate here that in terms of that percentage, then you will get something. I don't know what you'll get. I have not calculated that thing actually, but maybe if we calculate, like it is 2, that is 2 into like something 62.5 within that, then it will be something. How much it will be? It will be about 1.26, something like that, 25, something like that. So if it is that, then it is like this, and you can write it as 6.023 into 10 to the power 23 into 1.26 something by 12. And if you calculate it, then it will be something like 6.27 into 10 to the power 19 centimeter square per centimeter square. So that is the thing that you need to calculate here. So these are the process, and these are the mostly there is nothing. This is most likely the chemical reaction kind of thing which we used to do in the plus 2 level, like what will be in per mole inverse, per mole, or what will be in the per gram mole inverse. All those things you just need to remember those basic concepts here of plus 2 level, and you can calculate these things. And I found these things not very good because I don't like that much chemistry. So let us. So this is the thing that that is a and this is the thing that is the answer. That is answer is B, 6.27 in 119. And if you have to calculate, then you can calculate in this manner. And I would like that if you if when you will try in home, please do this thing. Calculate the thing, that percentage of carbon in molar. So though it will be provided to you mostly, but still try to calculate it. Now the question 2 is
Ma'am,
telling.
if I want to calculate the percentage of carbon,
Hmm.
then I should take carbon equal to 12, H equal to 1, O equal to 16, something like that. Per,
Yes,
per,
yes, yes. In terms of anything, if you can, I mean, 12C is equal to 12HY. Okay. Yes, that M into total nuclear, like the Z value plus N into N, number of neutrons, that value, and total mass, and all those things you can calculate. You can transfer it to the mass. You can do it in terms of energy or in terms of anything, because after all it is a percentage thing. So you will get the percentage because it is a fraction thing.
okay.
Now the thing is that it is telling that incident protons excite the 12 carbon, and de-excitation leads to the production of gamma rays. These gamma rays were detected using large cylindrical NAITI TL, that is scintillation detector, that you know already. This is also discussed with you, and in the detector part 2 class. And then the then it is telling that scintillation detector of radius 2 inch and length 4 inch, placed at a distance of 25 centimeter from the target. Calculate the solid angle subtended by the detector on the target foil. Again, I am focusing on the units. See there, radius of 2 seconds, and like you can see that there are very random units they are using. Like sometimes it is distance with centimeter, sometimes with inch, sometimes with something else. And these things are actually things which will make you wrong for the examination. I'm warning you for multiple times for the unit thing, because that is the thing that I also used to make mistake. So the thing is, now it is telling that incident photons excite the 12 carbon, and de-excitation leads to the production of gamma rays. All right.
Ma'am, the question is not visible.
Sorry.
Question. The question.
Okay, question is not visible. Okay, let me go to the question. All right. Question is not visible. All right. Now is it visible?
No, ma'am. The question number one is visible.
All right. I forgot.
Okay,
Uh,
now it is done.
okay, thank you. Yes, I forgot to change the slide. Okay, so question 2 is saying that incident protons excite the 12 carbon, and de-excitation leads to the production of gamma rays. These gamma rays were detected using large cylindrical NITL scintillation detector of radius 2 inch and length 4 inch, placed at a distance of 25 centimeter from the target. Calculate the solid angle subtended by the detector. So if it is the detector, then the solid angle subtended by the detector, that is that this is the theta. that you need to calculate. All right, if you want to calculate this, then this is you calculate a solid angle. For solid angle, you know the formula. I'll directly write the formula. It is 2 pi to 1 minus cos theta for whole solid angle. So you can calculate that solid angle thing for in a spherical coordinate, and that is a very standard thing for BSc level thing. BSc first year we used to calculate this solid angle subtended solid angle subtended by which amount and which theta amount. So that is the formula that I have used here. That is a 2 pi 1 minus cos theta, and then what is the theta? You need to calculate first. So for that you are given with the informations, like it is telling these gamma rays were detected using large cylindrical NIDL centralized detector of radius 2 inch and length 4 inch placed at a distance of 25 centimeter. So length is not important here. If we know the radius, that is the R, and the distance, that is the 25 centimeter, then what you can do is, then you can calculate the theta easily. Theta is equal to tan inverse. This theta is not this theta. Actually, what we used to do is not this one. Theta is this one, half angle, like the angle subtended by the radius and the distance. So this, if this is the theta, then tan inverse rate R, that is the radius, by the distance, if I call d, then R by d, then it will be tan inverse R means 2 into 2.54 centimeter, converting it from this unit to centimeter unit, and 2 centimeter, then you will be able to calculate it. 0.2032 is equal to 0.20047 radian. So now we need to calculate the solid angle. Solid angle equal to 2 pi 1 minus cos theta equal to 2 pi 1 minus cos 0.2032, sorry, 0.2047. If you calculate that, then you will get it as 0.1258 steradian, and the solid angle is given into the steradian unit. So that is what.
Ma'am,
Yes.
the answer is 0.1258 steradian. So should I convert it to steradian from radian to steradian, or it will automatically the answer is steradian?
Answer is steradian. We don't need to convert here because the solid angle is in steradian.
Okay, and tan inverse 2 into 2.5 by 2 centimeter, it should be 25 centimeter, is it?
Sorry, 25. By mistake, I have written 22. It will be 25.
Okay, okay.
Yes, thank you. It will be 25. Like this distance is 25 and this R is 2. So 2 into 2.54 by 25. Alright. So yes, so this is how we will calculate the solid angle. Now the next thing is question 3. Now whatever the background it is developing for this with these questions, that we will use in the next one question where all this information will be used. Now this is another question to develop the background, that is the question 3, which is saying that beam current of 10 nanoampere was incident, sorry, on the target foil for 60 minutes. Beam current is 10 nanoampere was incident on the target foil for 60 minutes. Calculate the charge collected by the charge integrator over the time of irradiation. What it is calling? Calculate the charge collected by the charge integrator over the time of irradiation. So this is simple. So this is a charge that you need to calculate over the time of irradiation. And what is the time? And time is given as 60 minutes. So if it is so, then the total amount of charge is nothing but, like, we know that dq dt is equal to I. This is a very simple plus 2 level concept again. And all the questions which I found, this detector level question or the kinematics level questions, those are all basic physics question actually. Those are nothing to do with the, like, some new thing, something new concept. Rather, which were taught in the in the first classes, like luminosity, all the stuffs in these, those were never taught to you or you didn't know. But here, whatever we are doing in terms of nuclear astrophysics things or nuclear physics things, those are all like basic course in basic physics things. So this is the dq dt, that is equal to I. Then if you calculate, then you know dq is equal to it. So what you need to calculate for calculating the charge is just it. So I is here the 10 nanoampere and t is here told as 60 minutes. But we need to get into the right units, that is the coulomb units. We need to convert these things, like we write this in terms of 10 nanoamperes mean 10 into 10 to the power minus 9 ampere, and 60 minutes means 60 into 60 second, that is like to convert in second. So ampere into second, that will give you in the coulomb. So if you calculate that, it is nothing but 3.6 into 10 to the power minus 5 coulomb. So this is the third question, and the answer is 3.6. That is A. Now the next question. Next question, it is telling that absolute full energy peak efficiency. Sorry, let me change the question. It is telling that absolute full energy peak efficiency of the detector at 4.43 mega electron volt, 9.64 mega electron volt, and 12.7 mega electron volt are 0.9%, 0.5%, and 0.01% respectively. The gamma ray spectrum acquired for 60 minutes consists of three major gamma rays: 4.43 mega electron volts of 1.2 into 10 to the power 5 counts, 9.64 mega electron volt of 3.2 into 10 to the power 4 counts, and 12.7 mega electron volt of 1.2 into 10 to the power 3 counts. Calculate the differential cross section of production of 4.43 mega electron volt gamma ray. How to calculate that? And for calculating these things, we need many information from the other part of the questions, like question 1 to 3, because this is the continuation of still whatever the thing we are talking about, that is the experiment it was talking about, that to study the interaction of proton with 12C experiment is being performed, and it is a continuation of that performed experiment which is told in question 1, question 2 and question 3, and now it is question 4. But this time it is, you need some I think this, I don't know if this formula is introduced with you or not, but this formula, again there is another formula for differential cross section calculation, and you have already calculated the cross section and differential cross section and sigma v mean, all those things. But this and it is like that only, but some different formula with some, like if you search for the differential cross section, then you will get the idea that how to calculate the differential cross section. It is nothing but that the cross section, and that is differentiated over the solid angle. So what you will get is the differential cross section, and here you need to calculate that. So the and all the informations that is given to, those are given to you in these or in the previous question. How that will show, we'll see. That is the first thing that you have understood, that it is we need to calculate differential cross section, which is equal to, which we denote as d sigma d omega. So this is the cross section and this is the solid angle. So as I told you the definition of the differential cross section, this is just showing that. So this is equal to yield by np nt omega epsilon. Yes. So yield is nothing but the number of counts of particles that is hitting, of the number of counts that is hitting. So here we are told to calculate the differential cross section of production for 4.43 mega electron volt gamma ray. Corresponding to these, the number of counts, that is the yield, is equal to 1.2 into 10 to the power 5. So we got the numerator part. Now we need to calculate NP, NT and omega epsilon. Epsilon is known, that will be given to you, that is just a factor, like form factor, and that is due to the impact thing, and that will be 0.009. That I forgot to mention in the question, that will be given to you. So epsilon is that. Now you need to calculate NP. What is NP? What is NT? And omega. What is omega? It is a solid angle. And you have already calculated the solid angle, that is 0.1258 steradian. Now you need to calculate the NP, which is nothing but the which is the total charge, like the calculate charge collected per unit electronic charge. That means we want to write the charge collection in terms of this will be, there will be no units as it is a number. So you'll get the number of amount of charge, like number of charge that we need to, like, which is the charge which is extra present there apart from the electron, because electrons are the charge that involved in this kind of things, but the extra charge, those are producing the gamma rays now. So that's why we need to calculate the extra charge. That is what is defining by this NP thing. So for that you need to calculate the NP, and it is nothing but the unit of number, because both numerator and denominator has a unit of coulomb, so it will give you a number. So if you calculate that, maybe we can write that is Q by E. Q is already calculated, which is what was that? Q is Q is 3.6 into 10 to the minus 5. 3.6 into 10 to the power minus 5. Yes. And electron is 1.6 into 10 to the power minus 19. This is coulomb. This is coulomb. If you write, then it is 2.25 into 10 to the power 14. Then you have to calculate NT, which is given over there. This is the NT part. NT is, omega is also already calculated, that is this. So NT is left. NT is nothing but the number of 12C nuclei present there, and that we have calculated as 6.27 into 10 to the power 19 centimeter square per centimeter square. So now you have NP, NT, yield, you have omega, you have epsilon, everything. So now we will calculate the differential cross section. That is equal to d sigma d omega, which is equal to, let me write the formula again for your reference so that you can like think this once again. So that is NP NT omega epsilon, which is equal to 1.2 into 10 to the power 5 by 2.25 into 10 to the power 14, that I calculated here. Now next is the NT, that is 6.27 into 10 to the power 19, that I have written here. And last but not the 0.1258 is a solid angle in steradian, and 0.009 is epsilon. And if you write that, then you will if you calculate that, then you will get 7.5 into 10 to the power minus 27 centimeter square per steradian. So now the answers are given in in the barn unit. So you need to change the unit. Again there is a unit problem. So this is a very heavy problem actually. I think this type of question will not come in your final examination. But still, who knows? Into 10 to the power minus 3 into 10 to the power minus 24. I can write 27 in terms of 3 and 24 because and it is still in centimeter square per steradian, because we know that one steradian is equal to one steradian, one centimeter square, that can be compared with the 10 to the minus 24 barn. So 7.5 into 10 to the power minus 3 barn per steradian. So now it is 7.5 millibarn per steradian. So the answer is C, 7.5 millibarn per steradian. So whole lot of things that we need to do for this question 4. So that is a question 4. Now the thing is question 5.
Ma'am,
Yes.
ma'am, here the values of NP and charge. We should remember those values.
No. You have just calculated, na? From those things I have taken this.
Current,
Like
so
Q.
charge.
This
But that's a different question, na?
I told na, this question 4 is continuation for this question 1 to 3. We are talking about the same experiment here.
Okay.
So you can get, this is just an example of that only, that if you may get some question which is a continuation of previous question. So these are question 1 2 3 4 and 5 will also be a inline question, and if you study them one by one, then you will get to understand that they are like that is just describing a interaction of protons with 12 carbon experiment with the with the where the gamma rays are coming from the solar flare, and with the satellite based gamma ray observatory it is calculating the thing. So this is the background of the experiment, and how it is going on. It is developing the question on the basis of those info for this experiment. That is the experiment is in the first question it is already told to you in the first 3 line that this is the thing that we are going to do, and now they are whatever the nitty-gritty they are doing, and with respect to that they are processing. So here in this question obviously I can tell on so this type of question may come that one experiment it is told in the first question, and the 1 2 3 4 other 4 questions is in accordance with that. But for those type of question, mostly they will write that this question this type of note will be there, that question 1 to question 5 are in sequence, or it will be written like that question 1 to question 5 are on the base of the same experiment. This kind of statement will be provided to the you during examination. So yes, so that is a thing, and now it is telling that calculate the total cross section. Calculate the total cross section of production of 4.43 mega electron volt gamma ray assuming isotropic angular distribution. Now you need to calculate the total cross section. Total cross section of production of 4.43 mega electron volt gamma ray, and it is considered isotropic angular distribution. That means there is in the with the change of theta there is no non-linearity. It is like whatever emitting in this everywhere it is similar, and if it is so, it is the ideal case, and for the whatever we are doing for the ideal case scenario only. So now you need to calculate total cross section. Total cross section, that is equal to sigma, which you can write as 0 to 4 pi d sigma d omega and over total solid angle. Like you need to calculate this cross section, and this is a solid angle. Now you integrate over this solid angle, then what remains to you is the d omega, d sigma, and that is if you integrate over the whole thing 0 to 4 pi. And why to 0 to 4 pi and all those things, I hope you have gone through those stuffs in BSc first year. When I was in bachelor's first year, I studied all those things like the cross section, solid angle. But I don't know about you. If you are not aware about these things, then you may visit any online sources or maybe Wikipedia. Also, they are the information that why this is like this, why it is this, why it is like this. So, but I found these stuffs are pretty basics, and I need to go to much more things. So I am not discussing that why I am writing exactly like this. So if you don't want, then you can also take this as a take home message, and the formulas, like we are using this kind of formulas. So after that we will get 4 pi d sigma d omega, that is equal to 4 pi into 7.5 millibarn, that I have calculated in that question 4. Like what that time it was telling that calculate the differential cross section. So if we calculate the differential cross section, then it will be like d is 7.5. It came as 7.5 milliborn. Then if it is so, then it is 4.5 into 7.5 milliborn, which will give you 94.25 milliborn, and that is the answer in question in option C. So, this was the like 5 question in synchronization. So, we have what we have calculated here. We calculate there is one scenario or experiment that is described to you, and for that they are talking, they are telling or asking you to calculate the how much they are to calculate the number of nuclei 12 carbon nuclei that is present in the target per centimeter square. Then what is the solid angle, then what is the total the charge for this beam current, and then what is the differential cross section and the total cross section. Now next question is question 6, which is like it is telling if the number of nuclei in the target foil is more reactions more, then more reactions will occur. If the number of nuclei in the target foil number of nuclei is more, then more reaction will occur. This will lead to what scenario? like number of in the number of nuclei in the target foil is more. That means there are many nuclei here, and it is coming there, and almost everyone is targeting some or other particles as there some or other nuclei, as there are many number of nuclei in the foil. So, will it change in the cross section or not? Because think in that manner, like it has like if I have this kind of scenario, that is target and this is the target foil, I have this number of nuclei, and I have this number of nuclei. So we are talking about the reaction cross section here. If it is like there are multiple particle bombarding over here, now the chance will increase, like everyone will target someone or other, because there are like and there will something will be there which will pass out, but there will be no nuclei left which will not be bombarded with the gamma ray. So that means there will be change in cross section. But if we are bombarding it and there are so many nuclei, so it will the like the reaction cross section, that means the reaction will occur, like it will it is becoming now the less numbers in according with the in term with respect to the number of nuclei present in the target. So there will be many target left over which will not be targeted by any bombardment. That means it will targeted by this, it will be targeted by this, and there are many left which reactions are not happening. So the cross section will not increase, reaction cross section will not increase. So what will be the scenario? No change in cross section. So, in this question, it is telling that if the number of nuclei in the target foil is increased, that means this scenario, then it will lead to which case? A, larger cross section value; B, a smaller cross section value; C, no change in cross section; D, change in cross section depending upon the material. So the answer will be no change in cross section. Now the question 7. All right.
Ma'am,
Hmm.
ma'am, in the summary notes you have provided,
Hmm.
and I have seen it at the last page. There is written lecture 1920. Not only last page, all the pages. Lecture means lecture
Oh, that
19.
is like that is like, don't go with that. That is for my reference. I use those things. So I have uploaded for like that. I have not removed that because that is how I was going with that. So that's why don't go with that thing. That is a
And,
summary.
and in the summary notes, all the lectures have been covered.
Yes, almost. Like we except the detector parts.
Except okay. That means except today. And
Except
okay,
yes.
okay.
All right. So apart from that, I have covered almost everything, and don't go with those lecture 1920. Those are like for me. And yes, I have covered all the topics are covered there apart from this detector part. Okay, so the next question is question 7. It is telling which of the following is a drawback specifically for the activity method. And this is like something which is taught to you. This is an informative question. You guys will know better than me because this is told to you, and this is just I think some of you can may give the answer also if you know, because it was discussed in the class by professor. But still I am if anybody is free if anybody wants to answer, then it's all right, write in the chat box, or otherwise I'll answer. So the question 8 is telling, in the time of flight method, the start signal is generated by, first option, the neutron detector, the gamma detector, the TSE module. Any one of the detector, neutron and gamma detectors can be used. So these are all informative questions which I don't like, but these are there, and these are given in these are there in the assignment 8 of your previous year's question, but this time I don't know if it was there or not. So yes, so the first question is that it's telling that what is the drawback specifically for the activity method, and this was told in the class. So the answer will be D, that is the product of the reaction should be radioactive. And question 8, it is telling, in the time of flight method, the start signal is generated by which detector? And the answer will be B, that is the gamma detector. Now the question 9, for the radioactive ion beam to be useful, the half-life of the radioactive ion should be significantly smaller than the transit time through the accelerating and transmitting sections of the accelerator. The half-life of the radioactive ion should be significantly large than the transit time through the accelerating and transmitting sections of the accelerator. It does not depend upon the nature of the radioactive ion. It cannot be an option that you can understand, because obviously it depends upon the nature of the radioactive ion. So C is already cancelled, and if C is cancelled, then and it is telling none of the above, D. Maybe that may be an option, but that is not so usual option that none of the above will happen. So we need to check for the A and B. It is telling that for the radioactive ion beam to be useful, the half-life of the radioactive ion should be significantly smaller than the transit time through the accelerating and transmitting sections of the accelerator. Accelerating part means that tube-like things, and then the transmitting sections, that is the gap between them. So it is telling half-life the radioactive ion should be significantly smaller than the transit time, and another one is saying that half-life of the radioactive ion should be significantly large than the. Okay, now this is telling about the transit time through the accelerating and transmitting section. Now this is the accelerating section, and this is the transmitting section. So if half life is less than this, like t half is less than the time it is spending over this region or this region, sorry. So yes, so if it is accelerating region or transmitting region, if the half life is lesser than their time spending during the accelerating or transmitting, that happens, that means the nuclei which we want, or the ion that is radioactive ion that is we are accelerating, that is not present there. That means some daughter nuclei has born already, but that we don't want. That means the half-life of the radioactive ion should be significantly large than the accelerating period and the transmitting period, such that it can go through the accelerator and we can get whatever we want. So the answer is answer B. This is a good question to get the idea that how the concepts the of those topics are used in an informative type question, or maybe this kind of questions used to be very manipulative questions, because this accelerator thing is taught to you, but maybe sometime how half life is comparable with this transmitting and accelerating thing, and what is the accelerating part and what is the transmitting part, that you need to figure out by visualizing that we have taught the accelerator and how accelerator runs, what is the accelerating part it may be calling, what is the transmitting part it may be calling, and if it is so, then the basic logic that if half lifetime is the less than the accelerating period or the transmitting period, then it will not be that nuclei, or that nuclei at that moment it will be a daughter nuclei, another nuclei. So it cannot be true. So what it need to be is the half life of the radioactive ions should be significantly larger than the transit time through the accelerating and transmitting sections of the accelerator. So this is the way that how you can reach your right answer for an informative type question also. This is, though it is an informative type question, but you need logic for this. 1 minute. And last but not the least, last question of this today's discussion session, and this nuclear physics discussion session. That is, last question is question 10. After that, we'll do the revision. It is telling, in the time of flight method, the stop signal is generated by the detector close to the neutron source, the detector far from the neutron source, the TSC module, the gamma detector. Again, informative question which were taught to you in the time of flight method in the last lecture. So the question it is telling is the time of flight method stop signal is generated by, and the answer will be B. That is the detector far from the neutron source. All right. So these were the questions for this week 8. Now we will do the revision for the total thing that we have taught, that were discussed in the class. But before that, maybe whoever is there at this moment, currently present, I would like to talk with them that like what you have, like what feeling you have, how is the preparation that is going on at your side, all those stuff. Maybe I can call one by one and you can tell that how much it is help for the with the tutorial sessions and the course content and the course work, and that will be like helpful for creating our next semester module, and also I can understand that how much it helped to you. So first, I can see from first is there is Manisha. So Manisha, do you like to tell anything like how is your preparation? Are you giving the examination, or what do you think about this course content, and what is your experience, all the stuff?
Mm, I want to sit for the exam, but the place is my third choice actually.
Okay.
So I'm not sure whether I'll be able to sit in the exam, but still I will try to go, and because I also attend this session.
Yes.
And regarding the course, the this discussion session has been very useful. But uh, the lecture PDFs which are given in the that, syllabus or with the module, that I have not. That means the write up of the video lectures.
Yes.
Uh, that I have not found very much useful. But these lecture sessions have been very useful for me. And even if I may not be able to sit for the exam, I think this is a good experience. This is a good learning experience for me actually,
Okay, that's very
and I
nice.
hope
Yes,
I hope to continue learning.
sure. And you are very much regular in the course. I have seen like every time you used to be
I,
there.
last two sessions I could not attend. One because of my the place where I was in, the network problem was issue was there, and one in one session actually I was not able to. But I have been through this in the drive you have provided.
Yes.
Thank you for that.
Okay. Okay. So all right, very nice. And then Nanda Kumar.
Ma'am, good evening, ma'am.
Yes. Good evening.
Ma'am, I am attending all the sessions for this the nuclear astrophysics problem solving session, ma'am.
Mhm. Yes, I
This
have also
course,
seen you. You are a regular student. Yes.
yes, ma'am. I previous semester I was applied for this examination, ma'am. The but I have not attended the
Come on.
exam, ma'am, because the
One.
computer office automation course
Yes.
was
Yes.
I was written in my district in my uh, I was written in that examination, ma'am. So I applied this session, ma'am. But the new solving session was introduced in the NPTEL, ma'am. This was very helpful for my learning in. This was very helpful for this session, ma'am. The
Yes. Yes.
the lecture course was a lot of some some lectures was uh, confusions, ma'am. But the problem solving session was easy to understand the that particular topics, ma'am.
Okay. Okay. So this time are you sitting for examination?
Yes, ma'am. This time I applied for examination, ma'am.
All right. So that's very nice. And so how is your preparation?
Ma'am, preparation was right going on, ma'am.
Yes, sure. Another 1 week is left, and that is, I think that will help you. And I have uploaded everything that you required. Maybe if you and any one of you need anything else, then let me know.
Yes,
Okay.
ma'am.
Okay.
Thank you, ma'am.
Okay. So next is spin two. Monisha, can you please turn off your mic?
Oh, so I'm so sorry.
Yes, yes, sure. So yes, spin to tell.
Yeah, good evening, ma'am.
Good evening.
Uh, um, I want to sit for the exam. I'm not sure because the NPTEL has not provided the admit card yet.
Okay, they
Just
will provide. They will provide.
and I am trying my best. And this type of live session is very useful for me. In spite of that, the lectures which are uploaded in Swam portal, that is not interesting. That is very much theoretical, and that is not very much useful for assignment solving.
Yes. Okay.
Because they are I think Swam or NPTEL modify the video lectures.
Mm-hmm.
It is not related to problem solving.
Yes.
Yes, that is my opinion also.
Yes, that I also found, and one time also Pinto, I think he told about this thing, and yes, this is absolutely I found this, but let's see what they do for next semester. But I tried my best to give for these discussion sessions.
And another one point is the live session is you know that the live session is 1 week lagging behind the
Yes,
current week.
yes, yes, yes. That is true. And other than that, like how is your preparation?
Yeah, I'm doing my preparation. Actually, ma'am, is it quite sufficient that if we go through the all the assignments problems?
Yes, assignment problems, the that for previous, that whatever I have solved and whatever you have got for your assignment these times, those questions if you practice and you understand all the stuff, then it will be pretty helpful for you in the examination.
Okay. And another question is, how many questions we should answer in
the
exam?
number
That
of
means,
the number of questions, they don't, I think anything regarding the examination they don't reveal, like NPTEL team don't reveal like the previous year's final examination question or final examination pattern. Anything you will not
okay,
get to know, and before the exam starts, the 15 minutes ago you'll get the details of all the stuff, that how many numbers of question you have to call. But you can think it that way, that it will be like gate or jam kind of thing. So 60 questions you can understand. If it is 3 hours question, 3 hour session, then maybe 60
yeah,
questions.
okay.
Okay, all right. So anything else, like okay, preparation is done. Okay, you are appearing for the examination too.
Yeah, yeah, yeah,
All right.
yeah.
Nice.
And,
And I
and
have given the
ma'am,
shared the book also. You asked me for that, and I
yeah,
became
yeah,
late.
yeah, yeah. I've got it.
Okay.
And ma'am, the Google Drive you have you have sent the link.
Hmm.
It will be active for up to NPTEL exam. The Google Drive.
Like now I have activated it for everyone. Whoever will have, like if you share someone this link, they can access it. Okay. But those who I have given personal, I have given permission beforehand, after the examination also they will have the they will have the permission.
Okay, okay, okay.
Like now for the due to the examination time, I have given permission for general body, like anybody can access. But if after the examination I will stop that, and those who with whom I have already shared and given the permissions, though they will be able to access it. Okay, all right. So and next is S Mohana Priya. Okay, I think she is not here, but okay. Let us continue with the revision part, or in case anybody else join in the in between, I'll talk with him or her in the at last. Okay, so let me go to the other things. The other thing is that the revision part, the revision. Okay, so for that I will write the formulas and what you need to remember, specifically what was the main thing that you have learned, and I'll go through all the slides. There are 105 slides with the questions. I will not visit again, but yes, there will be a recapitulate of this course totally, and in within 20 minutes to 30 minutes. Okay, maybe I will not take 30 minutes. Okay, so the revision. So the revision part, first we have started our course with talking about we're talking about the standard solar radius, solar mass, solar density, surface temperature of solar, luminosity of solar. All those are given in the lecture notes, like the discussion session notes that is given in the Google Drive folder. So these are the standard things with respect to which we will calculate anything if you want to calculate for the stars. Now the next thing which we learned is that metallicity, and we learned that there are mainly three things: hydrogen, helium, and metals in a star. And mostly it is about 0.70, that is a 70%, 0.28, that is a 28%, and 0.02, that is a 2% of metals. So this we learn. Then we go to the F by H, that is the iron by hydrogen ratio, which actually give you the metallicity rate. We calculate in terms of logarithmic scale. Then the formula is this. Then we learned about the Hubble, Hubble space Hubble constant. which is denoted as h, which is just nothing but the v by d, that is the velocity by distance. And we also, when we talked about this, we also calculated the Doppler shift, and we calculated the redshift thing, which is equal to z equal to delta lambda by lambda. Now the next thing is, we went to the radioactivity, which is like alpha decay. We enter into this domain: alpha decay, beta decay, and gamma decay. The expression, the alpha decay, beta decay, gamma decay, I have just discussed today also, so I will not go in detail of that at this moment. Then the point 6, we learned about specific luminosity of star. That is L nu, which is equal to del E by del T del nu. And I told that if anything is called specific, then it is in terms of unit frequency. If you are writing just del E by del T, then it will be only luminosity. Now, if you are talking about specific flux, then it is denoted with F nu, that is del E0 by del A del T del nu. Where del E, this del E is that amount of energy that is coming from the star, and this is the del E0 that is falling on the detector, the amount of energy. So these are two are different. So if you calculate and write all those things, and then you will get the relation between the specific flux and the specific luminosity, then you will get it as F nu is equal to L nu by 4 pi s square, where s is the distance. Now the seventh point is L is equal to 4 pi sigma r square t to the power 4. That we know, this is again the relation between, this is a Stephen's law kind of thing, and this is the relation with the r square and t to the power 4. This is a very important thing, and you may get a question from this. So if we write it, then it is log 10 L by L sun equal to C by plus 4 log 10 T by T sun. You can, if you know the temperature, you can calculate the luminosity and so on, and vice versa. Now we had the relation between L sun with the mass also, with some new in the as a power. So if you take the logarithm, then you get L sun equal to mu log of m sun. So this was the another formula and another concept that we learned. Then the 8, not point, maybe point 0.8 I can write, because this L proportional to the power 4 that is used many times. This is a Stephen's law. Question 9, we learned about the magnitude. Magnitude is equal to m, that is equal to alpha log 10 f plus c. Now m lambda is equal to minus 2.5 log f lambda plus c lambda. This is the volumetric magnitude integrated over all the lambda. Now you can write this in terms of L, that is a luminosity also, that is 2.5 log L lambda by 4 pi d square plus c lambda, and this is m lambda minus m lambda equal to minus 2.5 log 10 L lambda by 10 parsec square by L lambda by d square. Sorry, maybe I can write there. M lambda minus m lambda is equal to minus 2.5 log 10 n lambda by 10 parsec square by n lambda by d square. This is the absolute magnitude, difference between the absolute magnitude with the magnitude, and absolute magnitude is always calculated over the 10 parsecs distance. So if we do the difference between them, then we'll get that luminosity what is there within the 10 parsec and what is the actual. So for that we calculate we use this type of formula. Then the 10 point 10. Yes, point 10 is what we entered into the binding energy part, mass fraction part, mass defect, calculating the units, transferring the units, which is very important, and that is equal to del mn equal to m nuclear minus z mp minus n mn, and del E is then the this is the mass defect. Then del E is equal to del mn into c square, which is binding energy. And then we can calculate the nuclear Q value, which is Qn equal to mn1 plus mn2. Like if it is a reaction like 1 plus 2, 2 3 plus 4, then it is like this. Then Q value of the reaction, the nuclear Q value of the reaction is like this. So you can calculate that. Now we learned about the reaction, how to calculate binding energy, how to calculate the difference, how to change the units and all those stuff. Then we learned about the life cycle of star. We also learned about astronomical distance. What we learned that 1 AU, 1 light year, 1 parsec. 1 AU is equal to 4.84 into 10 to the power minus 6 parsec. 1 light year equal to 63241 AU, and 1 parsec is equal to 3.26 light year. Then we learned about the few important topics. Those are very important. That is elemental abundance curve. 14 HR diagram. These two these were discussed in great details, and I followed all the processes that how to get to the HR diagram. We have also discussed that how to understand the stuffs, like if you have one parameter, then how will you get to know that what is the temperature of it. If you know the luminosity, then how will you get to know that what is the temperature, surface temperature, what spectral domain that star will fall in, and if it is a main sequence, it is a red giant, it is a white dwarf, in which part of it will be, how to check those things. Though one questions are also there, was also there in your assignment regarding that. So HR diagram was a thing that I have discussed, and I also calculated the magnitude from the magnitude and the luminosity stuff, that how we ultimately reach to the consequence of HR diagram. Though it was an observation, it is an observational diagram, but we have some relations with which we can, if we know one thing, then we can calculate another thing, and what are the relations that we have discussed in great details in the discussion sessions. So after that HR diagram, elemental abundance curve, I write one formula which was related with the luminosity, radius, and the T, that I have written, but it is in terms of ratio. That's why I am writing again. Maybe it is a important, that because it is an important formula. This is just from that thing only, and all these are happening by considering the star as a black body. Then the then the point 16, we learned about cross section of nuclear reaction, and there were a lot of questions solved regarding the nuclear cross section and the mean of sigma v. Then we got to know that sigma is equal to basic concept is rp square, rp plus rt square, where this is the radius of the projectile and this is the radius of the target. Then we calculate, as I told, the sigma v, which is root over 8 by pi mu 1 by kt to the power 3 by 2, 0 to infinity e sigma e to the power minus e by kt dE. dE. We calculated, and there are many forms of this sigma v also. Those were discussed in the class, so you may check those also. Then the point 19, but this was the main fact of calculating sigma v min. Then point 90 is the number density, that is Ni, which is equal to rho NaXi by Mi. So that was a number density where Xi was the like mass fraction, Mi was something, it was Avogadro number, this was the density, all were discussed, and just visit this formula. Right now I am not writing that which parameter is denoting which thing, because those are discussed. I have shared the summary, I have shared the discussion session, all are there to you. Please go through that. And now we learned about the mean, and then we learned about the mean lifetime, which is 1 by Ni sigma v. 20.20 is r is equal to r0 to the power 1/3. 21, it is from nuclear size we got, and that is a very good important thing. And r0 is order of 1.2 into 10 to the power minus 15 meter. Then we learned about the liquid drum model, where we saw the binding energy, how it varies. So liquid drum model, this is the binding energy that we needed the correction term to treat the to better model the nuclei. For that, this is the volume part, this is the surface part, this is the Coulomb energy part, this is the asymmetry energy part, and this is the pairing term part. We discussed all of this, and we also derived the things, that how you got a to the power 2/3, a to the power 1/3, a z. These we calculated also. That was also discussed in discussion session. Liquid drum model. Then we go to the cell model, and several discussion was there with respect to the cell model. I have given you the cell model, the cell structures, and how to calculate the ground state calculation with the j value and plus minus value. These you can calculate now, that is the parity and the j value. So you have learned that as well, and those are there in, if you want to revisit again, please visit the YouTube or the Google Drive folder. Then we have talked about photo integration very briefly. Then we reached to another thing of sigma v. I forgot it to mention previously, that's why I have written there, that is the tau square e to the power minus tau, which is equal to t to the power tau minus 2 by 3, proportional to t to the power n, where n is equal to tau minus 2 by 3, that we discussed, and we solved problem related to this formula. So this was the another thing. And last but not the least, 25, that is the gamma peak width, which calculated as 4 equal to 4 by sigma equal to 4 by delta is equal to 4 by root 3 E0 kt. So these are the main formulas and main concept that we learned. After that, which come into play is that detector, accelerator, kinematics. These are the last two weeks, which where these are covered well in the lectures this time, and these are more towards like informative questions. And I showed whatever I felt that you need to know, that those I showed, like accelerators, what are the different types of accelerator, how it works, though, and so those are the things and that went for the last 2 weeks. And apart from that, up to week 6, these are the 25 formulas I have chosen very sincerely, the 26 things that you have learned. And not only these 26 things, you actually have learned so many things. I realized when I was making the summary part or the revision part, then I felt like this was a really like heavy thing, that we did a lot of things to learn new. And it was a very fun journey for me. It took lot of time from me, but at the end, if few persons have learned this, like I hope you guys will do very good in your examination. And that is what I need. And then it will be a very successful course, and I found this has run very pretty well. So let me go through the slides again. I'll tell that the in this course, the books that we talked about, that is the Iliadis that I have shared also, Rolls Rodney, Clayton, and all these were the main books. And this was the elective course. And week 0, I just made a video and and uploaded it in the YouTube, just to start it, that what do you want to learn. And I told you that the nuclear astrophysics is the union of nuclear physics and astronomy. And by now I think you have all understand that you have learned astronomy as some sort of astronomy and some sort of nuclear physics. There are a lot of discussion about both of the things. Then why you are doing this discipline has proved, because this discipline has proved to have the potential to categorize the condition at the core of stars and provide information of energy production stars and from stars and efficiency and stellar evolution. So these are the very important things, that nuclear physics and astronomy, they have evolved together, one helped another to evolve. So these are the week 0 questions, which are like class 2 level question or maybe less than that. And this is just to give you an idea that what you need to know basic like what the prerequisite you need. But at the end, now whoever have continued the total journey, they know that what thing we have learned. And those are literally very big topics, very quite involved topics which we have learned. So then we started with the background, observation astronomy, sun, star, galaxy, universe, elemental abundance curves, nuclear synthesis. Then we learned about the luminosity, cosmic microwave background, Hubble's constant, abundance elements, HR diagram. I'll not go to the questions, but yes, this was a CMB part. Then we talked about the carbonaceous chondrites meteorite, that is the first meteorite with which we know about the age. And then we talked about the element abundance curve. This was shown in your discussion. Then I gave you a short brief discussion about the Big Bang, stellar interior, supernova, nebula, in a solar structure, cosmic ray spallation, all those things. Then we also talked about the cosmic ray spallation and understand what is the nucleosynthesis process. Then we go to the velocity distribution, plasma, thermal energy, Q value, life cycle of star, luminosity, HR diagram, apparent and absolute magnitude, astronomical distances. And I told you guys that maybe I'll cover modeling of a star or may not, as per the time permits. But I am very happy that I was able to complete the modeling of a star also with some obviously the basic modeling, but it was covered with lot of discussion. So then we talked about this HR diagram. Then we checked that this is the total EM spectrum, which you need to remember very well, or you need to understand that to get the idea of whole astronomy or whole world, whole universe, you need to have the idea of whole EM spectrum. Because if you only see in the visible light, then you are getting some information, not all. When you will have the all information from long wavelength, the short wavelengths, the radio wave to gamma ray, then you can understand that what the nature is actually, how it is working. So then we solved the problems. Then we talked about the life cycle of star, how it is going from stellar nebula to white dwarf, neutron star, black hole, pulsar, and millisecond pulsars. All those stars I talked about those. Then we calculated the astronomical distances. Then the week 3 started. We come to the cross section, mean lifetime, and in between that we also talked about the liquid drop model, cell model, spin parity calculation of the cell model, photo disintegration, all those things, and solve the problems, and we reached to the week 4. And cell model and liquid drop model, those are not in slides; those are there in the detail. Those are discussed in the by writing in the writing pad. So the week 4 we discussed there was non-resonant charge particle induced reaction, astrophysical S factor, non-resonant charge particle induced reaction again, gamma peak, electron screening effect, resonant reaction, and those stuffs. So now we know about the cell model. We again I talked about the cell model. Now this time I talked about quantum tunneling because somebody has taught me that they don't know about the quantum tunneling, and I discussed that also. Then we go to the gamma peak Coulomb barrier reaction rate. So this was the photo disintegration process. Then we reached to the week 5. Week 5 it is telling about the it is telling about the neutron induced again non-resonant reaction. BP chain CNO cycle was the main factor in this week 5. And we have done miscellaneous problems. We have started miscellaneous problems from week 5 because by now the 50% of the course was completed. I have also shown you the NNDC website, which is a very useful website. You can play with it, you can check which kind of reaction is there, with what produce what, parent nuclei, daughter nuclei, gamma half, T half, what are the processes, what is the process by which it is, everything is there in NNDC, and it is a website provided by the Brookhaven National Library, which is regularly updated also. Then I have started the modeling of a star, that is also discussed, and that you can find in the Google Drive, in the class lecture notes, discussion lecture notes. Then the S wave, P wave, then the PP cycle, CNO cycle. Then I solved again we discussed about the questions, and we reached to the week 6, where we talked about the formation of 12C, that is a carbon. Then the burning nucleosynthesis beyond iron, SRP process. Then I go for the modeling of a star, continued, and revision and MCQ. Revision was important after that because this was approaching the final examination. So now we have solved the problems again. Then we reach to the week 7, where the charge particle accelerator detectors and the radiation sources, this come into play. And we talked about the accelerator. I saw the accelerator, which accelerators are there, and now how it is evolved and how it is worked, the basic model. And then we solved some problems. I talked about the exam details, which was shared by NPTEL team. And now today is the week 8, where there is talked about mostly about the detectors and kinematics of the nuclear reactions. But I go with with the summary and revision. And by this I hope the whole, and by acknowledge, and I also like to acknowledge these things for the running this course, and at the end I hope that everything whatever we wanted to cover and we wanted to do, that is successfully done and covered. And this is the nuclear astrophysics course, and that is what I want to say, and this is the thing that I wanted to give you from my side. All right. So formally, we don't have any other things to discuss today. So this is how we'll end after the class. And this is the I hope you guys have enjoyed, and you guys, most many of them have filled the feedback form. Those who have not filled, please fill. And YouTube channel is there to visit anytime. That will be there forever. So anytime if you find again, you can visit again. You can subscribe the channel to get more contents. Maybe this course is overing, but some new course I'll start again with the NPTEL, or maybe if also if it is not with the NPTEL, then with some other institute or something else. So you can get many more contents. And yes, if you find that these things are helpful, or maybe some short video will also be there after some time, just to discuss what is going on in the research right now. So for that you can subscribe, you can share, and you can whatever you want to do, you can check the videos later on also. So this was the the and the Google Drive folder. I Whoever is present right now in the class, I think all have the access. You will be able to access and share with your friends. You and at the end, I'd like to give you tell you all the best for your examination. All right. So, if you want to say anything, then please you are welcome. Otherwise, we will wrap up the session.
Ma'am,
Yes.
ma'am, yeah, if you face any problem regarding the solving,
Mm-hmm.
then
You can mail me.
mail.
Hmm.
Okay.
Surely you can mail me even if somebody is pursuing these things, and after overing of these classes, discussion sessions, or if this course this semester, you can also mail me if you find like if I can help you some in some way or other way for your for any discussion or anything. You can mail me.
Thank
All
you for your time.
yes.
Thank you for the whole sessions, for your time, for your effort.
Thank you for you also, that who have motivated me to take this class and end up this semester with like I literally found that I enjoyed the course with you guys. Like you guys have discussed, you guys have talked, you guys have sent me mail. Though it was a hectic thing for me, but at the end, if it is successful one, then that is the most deserving. That is the most interesting thing and most like awarding thing for me, that this has run successfully. So in that case, I think it is successful. It was successful, and yes, you guys were amazing. I like to talk with everyone, and some persons were there who have joined the classes regularly. Thanks to all of you.
Okay. Thank you, ma'am.
Okay, if anybody has not anything to say or nothing is left there, so let's call it as an end of this course, and let's wrap up the whole semester and syllabus and the discussion session. And once again, all the best to all of you. Thank you.
Thank you.
Thank you, ma'am. Bye.
Okay, thank you. Bye.
Thank you, ma'am.
Yes, bye.